All right, here's video number 2 for day 1. In this video, we'll cover horizontal asymptotes and limits as x approaches positive and negative infinity. We'll also look at continuity and intermediate value theorem. Okay, so let's start with horizontal asymptotes. This lesson or day is focused on limits. When we look at limits for rational functions or other functions, we're really talking about the end behavior. So as x goes to negative infinity, what's happening on the graph? As x goes to positive infinity, what's happening on the graph? For rational functions, we studied this in pre-calc. If you'll remember, we talked about expressions or functions being bottom heavy, top heavy, or balanced, and how that affects the horizontal asymptote. So as a quick refresher, you want to look at the degree in the numerator and the degree of the denominator. If the degree is smaller in the numerator, like if you had x squared over x cubed, your horizontal asymptote will always be y equals 0. That means if you're asked for the limit of that kind of function as x goes to positive infinity or negative infinity, it would be 0. If you have a rational function where the degree is the same on the top and the bottom, or the numerator and the denominator, you're going to look at the leading coefficients for the numerator and the denominator. So if you had 3x cubed over 5x cubed, your horizontal asymptote will be 3 over 5, because those are the leading coefficients. So that means if you were asked to find the limit as x went to positive infinity or negative infinity, your limit would be 3 over 5. If your degree in the numerator is larger than the degree in the denominator, so for example, if you had x cubed over x squared, there actually isn't a horizontal asymptote. Instead, there's an oblique asymptote. So the way you're going to handle this is you essentially, I'm going to add some numbers here. You essentially do this division just for the leading terms. Like if there was a 2 here and a -7, we'd ignore the 2 and the 7 and we'd just focus on these first two terms. And we would do the division. So this would simplify to 3x over 2. To do the limit, you are going to substitute in either positive or negative infinity. So here, I would substitute in infinity. And 3 and 2 are so small that they, are insignificant here. The limit is infinity. So on a graph, that means that your rational function is, maybe it looks like this, but as x goes to infinity, your graph is going up. Now, if this had been negative infinity in the limit, let me get a brighter color, negative infinity, then we would have substituted in negative infinity here, and our graph would go to negative infinity. So maybe this graph looks like this. So that's how you do limits as x goes to negative or positive infinity for a rational function. So as a quick reminder, we call this bottom heavy, top heavy, and balanced. You don't have to memorize those terms, but they're just a reminder from what we've done in the past. Okay, so take a quick minute, try the limits below, pause this video, and when you're done, check your work. Okay, so the first 4 should be pretty easy. 0, 2/3, infinity. Number 4 isn't a rational function, but it's one of the functions we said, or limits we said you should memorize. As a reminder, this oscillates, but it gets closer and closer to 0 as you go further and further out. Okay, for 5 and 6, a reminder on how we do shortcuts for that. So again, you're going to look at the leading terms here. The leading terms would simplify to 3x and the square root of x, 7x squared. Now let's think about simplifying this. So again, these are shortcuts. This isn't the formal algebra, but we've essentially got 3x over the square root of 7 times the square root of x squared, because we know we can split up radicals. Okay, then we can simplify this to 3x over the square root of 7 times x, and then our x's essentially cancel, and we've got 3 over root 7. It's 7. Okay, now this isn't a formal proof. Like we said, this is just a shortcut way to find what that limit would be. So it would be 3 divided by the square root of 7. Looking at number 6, it's nearly the exact same type of problem. There's one important difference. I'm going to back up to this spot before we plugged in infinity. So we said that this simplified to 3x times the square root of 7 times x. But in 6, our x value is going towards negative infinity. That would mean if I just left this as an x, I'd be plugging in negative infinity. But over here, you have x squared. The x squared is going to turn your negative infinity into a positive infinity. And then taking the square root of that. So this actually needs to be the absolute value of x over here, because it's not a negative infinity anymore, it's a positive infinity. So then think about plugging in infinity. You'd have 3 times negative infinity in the numerator, and in the denominator you have the square root of 7 times positive infinity. It doesn't look like a 7. Okay, there we go, 7. Our infinities are going to cancel, but that leaves us with negative 3 in the numerator this time, divided by the square root of 7. So our limit is negative 3 divided by the square root of 7. Okay, that's limits at infinity. Next up, let's talk continuity. So there are 3 key parts of the definition of continuity. A function f is continuous at c if f of c is defined, so if there's an actual value, if the limit of f of x as x approaches c exists, so the limit exists, and the value f of c exists and it's equal to the limit. So let's look at an example. We've got f of x, it's a piecewise function, and it's asking, is the function continuous at x equals 2? So first, does f of 2 exist? Is it defined? If I plug in f of 2 into this function, I need to look at my conditions over here. I would use or fit this condition because x is less than or equal to 2. So I'm going to plug 2 into x squared plus 3. So this becomes 2 squared plus 3, which is 7. Okay, so f of 2 exists. Now let's figure out what the limit of f of x is as x approaches 2. In order to figure out the limit, we're going to have to figure out what it is from the left and what it is from the right. So from the left, I'm going to use this top condition because when x is less than or equal to 2, we're looking at x squared plus 3. When x is greater than 2, we're looking at the piece 3x plus 2. So from the left, I'm going to plug in negative 2 squared plus 3. That's going to give me 7. Now let's do the limit as x approaches 2 from the right. I'm going to plug into 3 times negative 2 plus 2. That's negative 6 plus 2, which is negative 4. So, since the limit from the left and from the right are different numbers, we can conclude no, f of x is not continuous because, and I'm going to have to erase some of this other stuff, is not continuous because the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. And we're done. We don't have to move on to part 3 because we've already not met condition number 2. Okay, so the next 3 questions are ones for you to try on your own. Pause the video and then check back. Okay, so the first problem here, it said sketch a graph where number 1 is true, the condition number 1 is true, but number 2 is false. So an example for that would be, let's say you have a piecewise graph. So if this is x equals c, maybe your graph looks like this and is defined at x equals c, but it then jumps and goes somewhere else. The limit from the left would not be the same as the limit from the right. So number 1, f of c is defined, would be true, but it would fail the limit being, the limit existing. Okay, let's try the next one. Number 2 is true, so the limit exists, but the point is not defined. So similarly, this could be a piecewise function with a hole this time. So the limit exists because it's the same from the left and the right, but the function doesn't exist because there's no point at x equals c. So 2 is true, but 1 is false. Okay, final example. Let's make 1 and 2 true, but the point and the limit are different. So actually, leave it like this, where the limit is the same from the left and the right, and f of c is defined, but it's not the same as the limit. Okay, on to our next topic, which is the intermediate value theorem. And this is a relevant theorem here because it relates to continuity. So the intermediate value theorem says if f is continuous on interval a to b and k is any number between f of a and f of b, then there's at least one number c between a and b such that f of c equals k. Now that's a mouthful, so let's sketch a graph and see what the heck that means. Okay, so let's say we've got a here and b here. And at x equals a, you've got a point. And we're going to call this f of a. It could be any value. Let's say it's -2 on this graph. And then you've got f of b. That's at another point. We're going to say it's at 3. So this is f of b. And it says we have a continuous graph. So I'm just going to draw something that's continuous but looks a little crazy. We have met the definition that f has to be continuous and that we have an f of a and an f of b. Now the theorem says that somewhere between a and b there will be a value c such that f of c equals k. So choose a y value for your k. Let's say it's 0. We're going to make our k value 0. That means somewhere your graph hits that y value because this y value is between f of a and f of b. 0 is between -2 and 3. So in this graph, we actually hit that value 3 times. Let's say we had a simpler graph. Maybe this is just a straight line. Okay, so then here we're hitting k, or our k value of 0 at just 1 point. So this is our c value, wherever you hit k. So for any continuous function that has endpoints, so here f of a and f of b, if you choose a y value between those two endpoints, you have to hit it at some point. And that makes sense because your function is continuous. So you can't pick it up, it has to be a continuous graph, so at some point it has to hit every y value between your two endpoints. Okay, so let's apply that to a practice problem. So in example 1, it says we've got a table and f is continuous on the closed interval 0 to 2. The equation f of x equals 1/2 must have at least 2 solutions in the interval 0 to 2 if k equals 0, 1/2, 1, 2, or 3. So let's think about this. In this table, it looks like our endpoints are 1 and 2. So if I'm thinking about this on a graph, 0, 1, 2, my y values here are at 1 and 2. This is telling me that I want f of x to hit 1/2. But given the table information, we have points here and here. 1/2 is below both of these y values, the y value of 1 and 2. The intermediate value theorem says between these 2 points we can only expect to hit y values between here. So that means that we actually need to get a y value that is less than 1/2 so that 1/2 can be part of it. So if we choose 0, if we create a new point where it's 0, our graph is still continuous. It tells us f is continuous. Something's happening between here and here, and something's happening between here and here. Now we can use IVT on this interval between a y value of 0 and 1 to say that it must hit 1/2 at some point. And it will. It'll hit 1/2 there, somewhere in between. Then we can use IVT between 1 and 2, x equals 1 and x equals 2, that have a y value of 0 and 2, to say that it'll hit 1/2 somewhere between there. So this guarantees that f of x equals 1/2 has at least 2 solutions. It could happen more depending on how crazy your graph is, but that guarantees it. Now, why would B not work? So let's say we chose K to be 1/2. Okay, so let me draw back in our original points. We had a point at 0, 1, and 2, 2. If you chose 1/2 at 1, you would only guarantee a y value of 1/2 at that point. You can't guarantee that there will be 2 places where you hit 1/2, because in this picture you only hit it here. That's why you need a y value that goes lower, that goes down to 0, to guarantee you hit it on the interval between 0 and 1 and on the interval between 1 and 2. Okay, let's try another one. Example 2. Let f be a continuous function on the closed interval from -3 to 6. If f of 3 equals -1, so again, I'm going to draw a picture for myself, -3, and we're hitting -1, drawing a point, and f of 6 equals 3, drawing a point, then the intermediate value theorem guarantees, does it guarantee that f of 0 will equal 0? No, it doesn't guarantee any specific point at x equals 0. Does it guarantee anything about the derivative? No, it doesn't. IVT has nothing to do with derivatives. Does it guarantee that between a y value of -1 and a y value of 3, that f of x will be between those 2 values for all the points between -3 and 6? Now this is tricky. This might look like a correct answer, but it's not. The IVT doesn't guarantee that you have to stay between these y values. It just guarantees that you will hit every y value in between. But your graph could be going up and down and up and down. It doesn't guarantee that you stay between -1 and 3. Okay, so we can cross out C. All right, looks like we might need a new graph here too. Okay, let's check. F of C equals 1 for at least one C value between -3 and 6. Okay, so remember our lowest point was at -3, -1, and our high point here, our end point was at 6, 3. So this is saying, does it guarantee a y value of 1 somewhere in between x equals -3 and 6? Does 1 fall between -1 and 3? Yes. So that makes sense. And is it between an x value of -3 and 6? Yes. Okay, so our answer here is D. Why isn't it E? Well, it asks about guaranteeing a y value of 0. That would actually be okay because 0 is between -1 and 3, but it places it between the x values of -1 and 3, which is a much smaller interval. The IVT doesn't guarantee that it'll happen between -1 and 3. It guarantees it between -3 and 6. Okay, so that's all our review on limits, continuity, and the intermediate value theorem. You are ready for our practice problems and review in class.